In this lecture on radiation, we are going to study the directional nature of the radiation, and we are going to learn very important concepts like solid angle, intensity of radiation, view factor or shape factor. So till now, whatever we have studied, we have seen that suppose if this is a surface, and from that surface if radiation takes place, you know that radiation takes place in all directions, and we have defined the radiation flux or the total emissive power, right? So in total emissive power, the unit was watt per meter square. So here the total amount of energy per unit time per unit area that we have seen how to calculate from the surface. But suppose there is some other surface, let us consider another surface is there. Let us consider this surface, and we may be interested to know that how much heat from this surface will radiate and will go to this surface. Maybe we are interested to know how much radiation this surface will get, that is getting out of this first surface. So for that it is very important to know that the radiation that is taking place in different directions and how it is directly related to the total emissive power, that is very important, and that is why a very important property that we are going to define, and that is intensity. So the sole objective of defining intensity is to address the problems that in a particular direction how much radiation energy is going. To calculate that, it is very important to know how with the change of direction this is changing. And to understand intensity, the definition of intensity mathematically, you also have to understand the concept of solid angle. So that is why we'll start with the concept of solid angle, then we'll define intensity, and with the help of that we'll try to solve problems like this, that how much energy is going to cut the surface. And then for general case, it is very important to define the view factor. The idea of view factor will be defined at the end of the session. So let us start with the concept of solid angle. So as we know that in a 2D surface, how the angle is defined. In a 2D angle, we know, let us consider if this angle is theta, then if this radius is say r, and then this length, if this length is say s, we know that this theta in radian is defined as this arc length divided by r. This is in 2D how the angle is defined in radian. In case of 3D, the idea is instead of a circular arc, you just consider a spherical region. Okay, so if you consider a spherical region as shown in this figure, you can see this is a spherical area that has been considered. A spherical area has been considered, and that area divided by, if that spherical area, in this case a very small spherical area has been considered, so if that area is dA, which is a very small spherical area, so that spherical area divided by, if you want to find out what is the solid angle subtended by this area at this center, and if this distance is r from that center point to that area, then that dA divided by r square is the small solid angle that will subtended at the center. So this is how the solid angle is symbolized. Symbol of the solid angle used is omega. In case of a 2D angle, you know the symbol is theta. Okay, so similarly, if it is a finite area, instead of elemental small area, in that case that area divided by r square is what is the solid angle. But you have to remember, when you are considering that area, it may not be a spherical cap like that. Suppose you want to find out, let us consider this is one point, and you want to find out what is the solid angle subtended by this area. Okay, so in that case what you have to do, that in that case you have to consider from that point you just join this one. Okay, and what you have to do, you have to take the projected area, which is, you have to consider the projected area, that means which is the area which is normal to that direction, if that area is, if the red area is dA, and this area which is if this angle is theta, then this area is dA normal, which is basically what, that is equal to dA into cos of theta. Okay, so this is basically the area that will be DAN. So in finding out the solid angle subtended for this particular area which has been shown by red at this point, will be this DAN divided by, if this length is r, divided by r square. So this is what is the small solid angle subtended by that area. Okay, so the basic definition, I think it's clear. It is the normal to that direction. You have to consider the whole area. In case of a sphere, if you consider a spherical surface, you know that all the points are normal to that line, that is the radial line, because it is a spherical surface area on which we are considering area. That is why the formula is very simple. It is dA by r square. But if it is not normal like this, in that case what you have to do, you have to consider the area which is normal to that direction, and then you have to divide by the distance square. Okay, this is what is the formula by which you can find out the solid angle. And what is the unit? In case of 2D, you know the unit is radian, and in case of 3D the unit is steradian. Okay, so steradian is the unit for solid angle. So let us understand it in a better way. That means here you can see that small surface area on a spherical surface, as you can see, and if you consider that, if you consider this angle is basically what is the azimuthal angle, okay, phi, and this theta angle is what is the zenith angle, right? Because in case of a spherical coordinate system, it is r theta phi, by which we symbolize a particular point in a spherical system, and this is what is the azimuthal angle, and this is what is the zenith angle with this one. So if we just want to find out what is the solid angle subtended by this small area segment, and that small surface area, this dA is what, this length multiplied by this length, you can consider. So it's clear that if this length is r, so this is r, and this angle is what is the d theta. So what is this length? Clearly this length is then what, r d theta. That is why this is r d theta. So one of the side is r d theta, it is clear. Now other side, suppose you want to find out this one, you observe carefully the length, this length, particular length is nothing but the projection of this r on this plane. Okay, so what is that? That is nothing but r sine of theta, because this angle is, you just think in that way, that okay, this angle is theta, and you are projecting on the horizontal surface. So this is what is the horizontal surface. As you can see here, this is what is the horizontal surface. If we call it x and y, this xy is the horizontal surface. So the projection of this radial length on the horizontal surface, if this is r, this is theta, definitely this projection is r sine of theta. Okay, so if this is r sine of theta, then what is the small angle subtended? And that is d phi. So this length is r sine of theta. As you can see, this length is r sine of theta, and this angle is what is a d phi. So what will be this length? So this length or this length will be r sine of theta into d phi. Okay, so what will be that area? So that area actually written as ds. That ds is what? That is r sine theta d phi multiplied by r d theta, the product of these two. So this is what is the area. So from the definition of the solid angle, we know it is basically that area divided by r square, provided that area is normal to this r. In case of a spherical surface, since we have taken the area, definitely it is normal to r. So it is ds by r square. So if you find out ds by r square, it will finally reach to the formula that sine theta d theta d phi. This is what is the solid angle subtended in case of a spherical surface. Okay, that is now clear, I think. Now let's move on to the concept that here you can see the emitted radiation. Suppose we want to find out the how much radiation is going through in this small window, where this subtended solid angle, say d omega. Okay, so this is what is the idea of intensity, where this I basically indicate what is the intensity. So intensity is giving you the idea that per unit solid angle how much energy is radiating. Okay, so in case of emission, it is the how much energy it is emitting. Okay, so this is the basic idea of intensity, and that will help you to find out that within a particular angular window how much radiant energy will go. So that is why it is very important to define what we mean by the intensity. Okay, so the definition of intensity, as you can see, that it is basically if the energy, the rate of energy, here you can see the rate of energy is considered as the emission. If you consider the rate of emission, if we consider through a very small window as shown here, the rate of emission through that region is, if you consider dq. Okay, remember here this q, we are considering the unit is watt. Okay, so that per unit area, so per unit area normal to that direction, that is very important. So per unit area normal to the direction, here you see this area is a dA, but the direction that we have considered is at theta phi. This is what is the direction that we are considering. This is the direction we have considered at an angle, zenith angle theta, azimuthal angle phi. So this is the theta phi direction. So in that direction, what is the area normal to that of this area? Okay, so that area is this one, normal to that area. So definitely that area is a dA cos of theta. Okay, so this is what is the normal area in that direction. So dA cos theta. So this is what is the rate of radiation that is going out per unit area, which is normal to that direction, per unit solid angle. Okay, so per unit solid angle means divided by d omega. So around that direction, if you consider a very small solid angle around that direction, if that solid angle is d omega, then this is what is the definition of intensity of radiation in that direction. Okay, so this is what is the total intensity. We are not considering the spectral property. You can also define the spectral property, that means per unit wavelength. So in that case, what you have to do, you have to divide the expression by d lambda. Okay, and in that case it will be spectral intensity. But let us not consider that spectral intensity. Let us consider the total radiation intensity, and that is defined in this way. Okay, so this thing actually has been shown here. As you can see, this is what is the emitting energy in watt, that divided by dA cos theta, which is the normal to that direction, divided by d omega is the solid angle around that particular direction. And remember, this intensity which has been defined here is function of both theta and phi in general. In general, they are function of theta and phi. Okay, so now you see that the expression, if you just put the value of d omega, we have already defined d omega as sine theta d theta d phi. So you just put that value of d omega, you can get a relation that how much energy will actually go through in that small window. Suppose we want to find out that how much energy dq will go through that window, how much watt will go through that window. So if you want to find out that dq, so what you have to do, you have to just consider the intensity in that direction multiplied by the area which is normal, that is dA cos of theta multiplied by d omega. Okay, so this is what is the small dq going out. Now if you want to find out that what is the total, that means if you integrate over the whole surface, over the whole theta and phi, and then if you just put the value of d omega, that means I into dA cos theta into d omega is, you already know, that is sine theta into d theta d phi. And if you integrate this quantity over theta and phi, so that it covers the whole surface, that means the whole hemisphere, it will cover the whole hemisphere, then it will give you the total amount of energy that is coming out of this particular surface, okay, of dA in all directions. Okay, so if you want to do that, you see that what is this theta and phi are going to vary. It is clear that theta, if you vary from 0 to 90 degree, if you vary theta from 0 to 90 degree, it will be like this kind of thing. And then if you just rotate this thing by 2 pi, then it will cover, it will produce this hemisphere. So for the theta, it is 0 to pi by 2, and for the phi, it is 0 to 2 pi. So within this window, if you do this integration, you will be able to find out what is the total energy. That means you can find out what is the total energy that is coming out in all direction in the whole hemisphere from that surface dA. Okay, so that can be done, and as you can see here, what has been done here, dq divided by dA, which is what is known as the flux, instead of which is what is the flux that is coming out from that surface. And if you want to find out that quantity, the total flux, this is what is the dE, the small flux. And if you want to find out the total flux, and that total flux will be integration of this quantity. Okay, so already we have seen the expression of dq. We have divided by dA because in the expression you see that this particular quantity dq by dA is what is dE. Okay, so this quantity is dE. So whatever is there in the bottom, that means in the denominator remaining, if you multiply that with this quantity, then that quantity is IE that means here only emission is considered, so that is why the symbol E into this bracketed term, that is cos theta sin theta into d theta into d phi. And if you just integrate this quantity over the whole theta and phi, then you will get the total emissive power that is coming out in all directions. And what will be the range of theta and phi? I think it's clear. Theta will vary from 0 to pi by 2 and phi will vary from 0 to 2 pi. And if you do this integration, and you will get the result that has been shown here. It's very simple. Only thing is that, you see, I have already told you that this IE, this intensity, is in general function of theta and phi. In general they are function of theta and phi, but for some special surface which is independent of the direction, like this I theta is not depending on theta and phi, and which is constant. So I is constant and not depending on theta and phi. That means this intensity is independent of direction. Okay, so if this is the condition of the surface, then that surface is called the diffuse surface. Okay, so that is called a diffuse surface. So in case of diffuse emission, you can consider this particular quantity is not function of theta and phi, and you can take this quantity out of this integration. Okay, if you take this quantity out of the integration, then the expression will be I into integration of this quantity, remaining quantity, right? And the remaining quantity integration is what? You see that d phi is not there. So d phi, if you integrate from 0 to 2 pi, it will give you 2 pi. Okay, and what else? 0 to pi by 2 sin theta cos theta d theta. So you can convert it into half into sine of 2 theta into d theta from 0 to pi by 2. And if you do this calculation, sine 2 theta integration is minus cos of 2 theta divided by 2, and if you do that and if you put those values, you will find your final expression will be pi into I. Okay, so that means we are getting a very interesting result. That means the intensity, how it is related to the total emissive power, and the relation, if it is over the whole hemisphere, if it is integrated over the whole hemisphere, the multiplying constant which is coming as the pi, remember this pi having dimension steradian. Okay, so the relation is E is equal to pi into I. If it is a black body, if the surface is a black body, in that case this E will be EB and I will be IB. That means intensity for a black body, and this is the black body total emissive power. That's all. But the relation, this pi steradian, is basically coming because of the integration over the whole hemisphere. Okay, so this is a very important relationship, and already I think you remember what is EB. If it is if the surface is isothermal surface, you know that this value already we know from Stefan-Boltzmann constant is sigma T to the power 4. If it is a black body, it is sigma T to the power 4. If it is a gray surface, you can consider it is epsilon into sigma T to the power 4 E. So E and EB, I think is known to you if you know the temperature, and intensity is directly related to that. So you have to just simply divide that quantity by pi and you are going to get what is the intensity. Okay, so straight away finding out intensity is basically, if you know the surface temperature, so find out what is E and divide by pi, you will get the intensity. Okay, and similarly for black body radiation, if it is EB divided by pi, you will get IB. Okay, Now coming to practical problem, let's see that we can address this problem or not. Let us consider there is one surface which is A1, which is given, and its temperature is given 600 Kelvin. And what we have to find out is that there is another surface, here you can see A2, which is 5 centimeter square, and we are assuming that the surfaces are small. As you can see, it is 3 centimeters and 5 centimeters, but the distance between them is 75 centimeter. Since 75 centimeter is quite a long distance with respect to this area, as you can see, so we can consider this to be very small surface. Now what we have to find out is basically determine the solid angle subtended by A2 when viewed from A1. Solid angle subtended by A2 when viewed from A1. So since we are considering these as small surfaces, so basically let us consider this centroidal point and this centroidal point, and if you just connect, this is what is R, and that R value is known. What you have to do, you have to know that the formula of the solid angle is basically find out the normal area. Find out the normal area. Here, this is what is the normal area. I'm showing by the red, this normal area, and that normal area divided by R square will give you the solid angle of 2 if viewed from 1. Omega 2 1 indicates that solid angle of area 2 if viewed from 1. Okay, so it is very simple. A2 cos of theta, A2 is given, theta is known. Okay, theta is basically with the normal, what is the angle, and divided by the R square, that means this distance. So solid angle you can find out. Here you see the unit is steradian. Now the second part is that you have to find out that the rate at which the radiation emitted by A1 that strikes A2. So how much radiation emitted from A1 and strike A2. So for that you have to find out the intensity in that direction. You have to find out intensity in that direction. If you can find out intensity in that direction, then what you do, simply that intensity multiplied by the normal area, this normal area which is A1 cos theta, normal area, this one multiplied by the solid angle in that direction, that is omega 2 1, that we have already calculated. A1 cos theta, theta and A1 are given, so only thing you have to find out, that is intensity in that direction. So we know by the time that how we can find out the intensity, since we are considering it is a diffuse surface, so in all direction the intensity is same. So just find out the intensity considering this A1 surface as the black surface. Okay, I think in the problem it has been mentioned that A1 is a black body. Yes, A1 is a black body, that has been mentioned. So you know that how we can make use of this formula, that EB is equal to pi into IB. We have just seen this formula, so using that you find out what is IB. So EB, you know from the Stefan-Boltzmann law, that sigma T1 to the power 4, and divide by pi, you will get the intensity. Okay, so once you know intensity, just put the value of intensity and you will get that in watt how much energy will strike surface 2. Okay, so this is the way we can actually solve the problem. I think the concept of the solid angle is very important, and the concept of the intensity is very important, and now you see we can address the problem, like if some surface is there and here is some other surface, so how much energy will strike this particular surface. But here we have considered these surfaces are very small. These surfaces are very small. This is what is the assumption that we have considered, because the distance is very large. But what will happen if the surfaces are large? In that case, that we are going to see definitely, and that is why the concept of view factor will come into picture. Okay. Now view factor, this particular concept is again basically if you consider this is a particular surface and let us consider this blue one is another surface, and they are large surfaces. Let us consider they are not small surfaces. So how you can find out that the main objective is that how much radiation will strike this particular surface. Okay, because final objective definitely will be how much will be the heat exchange between these two surfaces, that we are going to address in the next lecture. But in this lecture we will see that how much is going to strike. So view factor is something which is defined as a ratio. It is defined as the ratio of how much thermal energy in watt is going to strike the surface divided by the total amount of energy radiated from this surface. So this is what is the idea of view factor of these 1 to 2. Okay, so if you consider this surface is 1 and this surface is 2, so what is view factor is that how much energy is striking surface 2, that means how much energy leaving from 1 and striking 2 in watt divided by the total amount of energy radiating out of 1, that means what is Q1. Okay, so this particular ratio is called the view factor, which is generally symbolized by F from 1 to 2. This is what is the view factor F from 1 to 2. So this is what is the idea of view factor. Okay, this ratio is called the view factor, or sometimes it is called the shape factor. Okay, and this can be shown, we are going to show it, that this is completely a geometric parameter. This is completely a geometric parameter, and this view factor is not depending upon their temperature or other things, surface properties or anything. It is completely the geometry and the orientation. It depends only on that. Okay. So here is the idea. Already we have discussed that if 1, 2 is basically view factor, if you are looking from A1 to A2 is equal to the rate of radiation energy striking, leaving from A1 and striking A2 divided by total radiation energy coming out of A1. So this ratio is called the view factor 1 to 2. Okay, so if we want to find out this ratio, it is very simple because already we have seen that how to find out the radiation between two elemental surfaces if the surface area is very small. So let us consider A1 is this finite area and A2 is this finite area. So this is A2 and this is A1. Now consider within A1, if we consider a very small area dA1, and within A2 if we consider a small area dA2, then these are the normals. N1 of dA1 and N2 is the normal on dA2. So let us first find out how much energy will strike this small area leaving from 1 to 2. Okay, so this quantity suppose we want to find out. So what we know, so it is very simple. Find out the intensity in that direction. If you just join the centroid of these two are elemental. So if you just join these two, then in that direction, if the intensity is I1 multiplied by cos of theta 1 into dA1. What is cos of theta 1 dA1? Because the normal area that you have to consider, you know, that intensity multiplied by the area normal to that direction, that you have to consider, multiplied by W21. That means if you look from 1, how much, that means you are looking from 1 and how much is the solid angle that you will observe. So, or 2 will subtend the solid angle at 1. So, W21. And dW21 already you know how to calculate that. You have to take the normal direction. That means this is the dA normal that is dA to cos of theta 2. In that case, this is divided by r square, where this length is r. Okay, this length is r. So this is what is the solid angle part. This is the area which is normal, where from the radiation is coming out, that means dA1. So the normal to the direction r that we have taken, multiplied by the intensity. So this is what this quantity. Now what you have to do, you just integrate this quantity over A1, the whole surface. That means if you integrate over the whole surface, and if you integrate over this whole surface A2, then we will get the rate of heat transfer from the finite surface A1, and that is going to strike the finite surface A2. So this quantity. So if you do that, then the expressions will be like this, and you see carefully what is this particular quantity. So let me show you that this is what is Q dot A1 to A2. Now let me show you that what is Q dot A1 now. So this numerator part we have seen here. This is what is the numerator part. You can see this is what is the numerator part, and a numerator part we can also write in this way as, what is this I1? Tell me, what is this I1? This I1 is basically this E1 divided by pi. Clear? Because I1 is equal to E1 divided by pi, because it is over the whole hemispherical region. So you just simplify this I1 as E1 by pi, then its expression will become what? It will become okay, I am just doing it here. So it will become E1 divided by pi. So we have just replaced I1 by E1 divided by pi, and as we are considering this E is not depending on the area, or this I is we have considered as the diffuse surface. So we are just simply considering the uniform property of E over the whole surface. It is not that from one point to another point the value of E is changing, because actually to integrate over the whole area you have to consider the small dA, small dA, small dA, and you have to add all these things. So we are assuming it is the uniform E over the whole surface. So if that is the situation, if it is a similar surface throughout everywhere, the properties are same, then this E will just simply come out of the double integration, or I will actually come out of the integration, and then you put the so the expression will become for the net rate of heat transfer is basically E1 that will come out of the integration, and this. Now you see this is what is the expression then. So then the expression becomes E1, and then I1 will not be there, and there will be pi r square. Okay, and now if you divide by QA1 dot, how much is the total energy coming out from this, that you can easily find out the total emission that will come out is nothing but A1 into E1, right? A1 is the into E1 is the total thermal energy, because this is what is the flux multiplied by the area, then its unit will be in watt, right? So A1 E1 is basically the denominator part. So if you divide to find out this view factor, you just divide this quantity by A1 E1. If you divide the quantity by A1 E1, then you see that E1 will cancel and A1 will remain. Okay, so I hope you can understand. Here E1 is there, and you have divided by A1 E1. Okay, so E1 will cancel, and it will become 1 by a1 into integration of this part. So this is what is the view factor from 1 to 2, where a1 and a2 are two finite surfaces. Okay, so this is what is the view factor. So now exactly in a similar way you can tell that the integration having a similarity of f12. So you can see that what is f21. You can easily say f21 exactly in a similar way will be a1 by a2. In the same integration, the remaining thing within the integration will remain same. It is not going to change because it is so symmetric with respect to 1 and 2. Right. And I think you can understand that there is a relationship that we can develop, that a1 into f12, that is basically this symmetric integration. Okay, so it is clear that a1 f12, this quantity here is exactly same as if you multiply this a2 with f21, a2 into f21. So these two things are same. Okay, so this is one of the very important relation in the view factor, and this particular relation is called the reciprocity relation. Okay, this is called the reciprocity relation that you can see here. And I think the concept of view factor is clear, and definitely view factor helps you to find out the heat transfer in a particular orientation, in a direction that we are going to take up in the next lecture in detail. But let us see how to find out the view factor. Don't you think that this integration is very difficult? Yes, the integration is really very difficult. This r is function of very much theta 1 and theta 2. You can understand that the small areas if you take, and these r are going to change continuously. Solid angles are going to change. That means this theta 1, theta 2 continuously change. It's a very, very complicated integration. It's not simple integrations. Okay, so to finding out view factor every time you have to do this complete integration. It seems that you have to do this integration, but you have to remember that with some tricky ways, with some for some certain simpler surfaces, it is possible to find out some simple geometry and algebra. We can find out the view factors. Okay, all the time we do not require to do all this integration. So what we can see is that if I to j, if we are talking about two surfaces, one is I surface, another one is j surface. So if I to j is the fraction of the radiation leaving surface I that strikes surface j, that we have understood. Now some important points. The view factor ranges between 0 to 1. It is quite clear, it's a fraction. The maximum amount that is coming out from 1 is q1, qa1, and definitely a fraction of it will strike this surface. So this quantity definitely is less than 1 and minimum 0 if they are not facing each other. Okay, so it is a number between 0 to 1. It's a fraction. Clear? Now Fij is equal to 0 indicates that the two surfaces do not see each other. Okay, if Ij is 0, that means the surface, the energy that is coming out from a particular surface is not going to strike the other surface. In that case only Fij is equal to 0. And when Fij is equal to 1, Fij is equal to 1 means the whatever radiation is coming out from one surface definitely will strike the other surface. And these things may happen if let us consider this is a spherical surface 1, and consider there is another surface that is 2, which is completely enclosed. This surface is completely enclosed by 2. In that case, definitely whatever is coming out from 1 definitely strike 2. So we can say in this example that F12 must be is equal to 1. There is no other choice. F12 must be is equal to 1, because whatever is coming out of 1 must strike 2. So F12 is equal to 1. Okay. Now the radiation that strikes a surface does not need to be absorbed by that surface. It is true that the radiation that will strike a surface does not will absorb completely, because there may be some portion that will be reflected back and again come into this surface 1 and all that. Okay. Now if II means from surface 1 to 1, that means this is a self view factor. That means what is the meaning of F11? F11 means some radiation coming out of 1 and will strike 1 again. That thing happens in case of concave surfaces. Let us consider this situation 3 figure that you can see, that concave surface. So here you can see some radiation is coming out, okay, but this radiation you see again strike the same surface 3. So in this example you can understand this surface, if this surface is called I, this surface is called I, then Fii definitely is a non-zero quantity. It is not that so it is facing a cave surface. Remember, Fii is non-zero, but if it is a plane surface, there is no chance what is coming out from surface 1 is not going to strike 1. So Fii is 0. In case of a convex surface, definitely Fii is 0. Whatever is coming, definitely not striking again. But in case of a concave surface, you have to be cautious. Okay, Fii is non-zero. That you have to remember. Now, definitely for certain situations, like suppose some simple situations, suppose this is a rectangular plate, this is another rectangular plate, and the dimensions like x and y and the distance between the rectangular plate, if that is L, in that case the view factor after doing that complicated integration, it can be shown is by this formula. So you can understand it's a very complicated formula to final result. To remember this formula even is very difficult, and doing integration is definitely difficult. So one can do in that way is that we can make use of chart to find out. Basically this results has been plotted in the form of a chart, where you see in the x-axis it is the ratio L2 by D, where L2 and L1, that you can see in the chart, that what is L2 and what is L1. So for the particular dimension, you find out what is L2 and what is D. D is the distance between them. L2, L1 are the two dimensions of the rectangle. So in the x-axis, you find out L2 by D. Then these are L1 by D. The different curves you can see here, each of the curve corresponding to a particular L1 by D. So for a particular problem, you find out what is L1 by D, select that appropriate curve, and then you find out what is L2 by D. So from that you find out what is the value of view factor directly in the y-axis. Okay, so this is the way you can find out, make use of the chart to find out the view factors for certain kind of orientation, that you can see to parallel plates here. Similarly to parallel disc, this is the algebraic formula. Two plates, as you can see, making an angle between them. It is a 90-degree angle, perpendicular rectangle. So in that case, this is the formula. So each of them having their separate charts. As you can see, this is the chart corresponding to that. Similarly for the disc, there are charts available in the handbook. So you can make use of this chart to find out the simple geometrical orientation. Now see that how many view factors actually we have to solve if there is some enclosure. Okay, so the technique is that to finding out the view factors between two surfaces or something. So we use the concept of enclosure principle. In enclosure strategy is that every surface or a set of surface can be considered as some enclosure with some additional surfaces. Let us consider this is an enclosure. That means that enclosed. So there are how many surfaces? 1, 2, 3, 4, 5. So it's a 5 surface enclosure. If you consider this one, this is not an enclosure. There are 3 surfaces, suppose. So what we do, we simply consider another surface which is shown by the dotted line, and we'll make an enclosure out of it. And we'll consider this is having temperature as T infinity, and you'll consider it is as emissivity is equal to 1, and we'll treat in this way and we'll find out the view factors. Okay, though for the view factors you do not need all these quantities, but this is the way we actually finding out the view factors. So we'll consider the enclosure and then we'll solve the problems. So now let us consider, so any surface, let us consider this is one surface only. So what we do, we'll consider another surface and we'll make it an enclosure and then we'll solve. So this is what is the idea. Okay, now question is how many view factors are there in an enclosure. If there are say n surfaces in an enclosure, if there are n surfaces, then how many view factors that we have to solve. So if there are n surfaces, then there will be total n square number of view factors. Why n square? It's clear. If you just want to write in the form of matrix, you will understand. Say F11, sorry, F11 F11 F12 in this way F1n. Now you see F21 F22 F2n, and in this way Fn1 and finally Fnn. So you can see there are n square number of total view factors that you have to find out. Now the question is, all these view factors are not independent. So how many independent view factors you actually have to find out? So for that we can make use of the reciprocity rule. Already we have seen what is reciprocity rule, that for two surface 1 and 2 we have seen that A1 F12 is equal to A2 F21. Similarly, for any two combination I and j, this is true that AI Fij is equal to Aj Fji, right? So now the question is how many such equations you can form if there are total n number of surfaces. So it is clear that for any two combination you will get one such reciprocity relation. So there are total n surfaces. So how many ways you can select two particular surface? So nc2 ways. Okay, so there are nc2 number of reciprocity rules. nc2 number of reciprocity rules are there. So these are kind of constraints already there. So that means all these n square number of view factors are not independent. Next is the summation rule. By summation rule is what? It is clear that suppose there are three surface enclosure. And this is 1, this is 2, and this is 3. So it is clear that F11 plus F12 plus F13 must be is equal to 1. Because it is an enclosure, so definitely whatever energy is going out from 1, it will either fall in 2 or fall in 3, or it will go to 1 if it is not a plane or a convex surface. Okay, so you can understand that this summation of these will be is equal to 1. Similarly, for each surface, what you can consider that, let us consider this is surface number 1 and there are n minus 1 other surfaces. So definitely F11 plus F12. So summation of this row, basically the summation of this row is basically is equal to 1. Summation of this row is basically is equal to 1. So these are basically the summation rule that we can apply. So these are certain constraint equation here getting. So how many such equations are there? Definitely there are n rows, so you will get n such equations. So there are n such equations. So total n square number of view factors possible in an enclosure of n surfaces. Then out of them NC2 are reciprocity relations are there, and n summation rules are there. So how many independent then remains? It is n square minus NC2 minus n. Okay, so if you just simplify these quantities, you will find that it will again come NC2. You just simplify it, because NC2 is what? N into n minus 1 divided by 2. Just put this expression here, simplify this algebra, you will find the result is again n into n minus 1 by 2. So NC2 is the total number of independent view factors possible. So that has been done, and you see that finally you are come up with the result. The independent view factors is n into n minus 1 by 2. Now let us see some of the problems to find out the view factors. Okay, so here the problem is there are three situations given, 1, 2 and 3, and each of them you have to find out F12 and F21. So the first one is the sphere of diameter d inside a cubical box of length L, such that which is equal to the diameter of the sphere d. Okay, so it's a box. So it's a box, and here is a sphere. So this is the sphere, and here is the box. So what you do, you just consider this spherical surface as 1. You just consider spherical surface as 1, and this box surface is as 2. So separately we are not considering each surface, so we are considering all this surface as a whole as 2. Okay, so this is what is the total surface that we are considering. I am just showing from the front view. Basically the surface is like this, as you can understand. So this is what is the surface we are considering, 2, and 1 is basically the outer surface of the sphere, you can understand. So now what we can write about, you tell me what is F11. Whatever is radiating out of 1 definitely will strike 2, right? It is a convex surface. Okay, so whatever is coming out of 1 will strike 2, because it is completely enclosed by surface 2. So definitely F1 to 2 is equal to 1. There is no doubt. Whatever is going out of 1 must strike 2, because 1 is convex surface. That is why F11 is also 0. So that is why F12 is equal to 1. I think it's clear. Or you can make use of between 1 and 2, you can apply this formula, that F11 plus F12 we know from the summation rule is equal to 1, and F11 is equal to 0, because 1 is a convex surface. So in that case also you are going to get the same thing, F12 is equal to 1. Then what you have to find out, what is F21? To find out F21, you can use the reciprocity relation. What you know? A1 F12 is equal to A2 F21. So already you know F12, which is 1. You know what is A1. A1 is what? 4 pi r square. You just express in terms of d. A2 you know. A2 is the total surface area of the box, that you can easily find out if the length is L. So each surface is L square. There are 6 surfaces, so 6L square. So I think you can do that. And what is F21? Then you can easily find out F21 will be A1 by A2 into F12, which is 1. So do this calculation, you will get F21. Okay, it is simple geometry. Without any integration, you are able to find out this thing. Okay, coming to the next problem. So that thing is the first problem has been shown here. The final answer is this one, and using this you can find out what is F22 also. Maybe this problem was there, F22, no, that was not there, but if you want to have to calculate what is F22, because F22 you can see that 22 is not non-zero quantities, so you can use the summation rule. F21 plus F22 is equal to 1. So once you know what is F21, make use of this formula and find out F22, that is 1 minus this. So that has been done. So this problem is basically a squared duct. So this is a squared duct like this, and in that duct there is a partition here, diagonally placed a partition, and that surface is also gone along the length of the duct. Okay, so this is what is the partition, and this surface, the partition surface, is considered as 1. This side surface is given as 2, and this surface is suppose 3. Okay, so what you can do here, the first thing you can do is that you can make use of the summation rule, that 1 2 2 1 2 3, because F11 is 0, so F11 plus F12 plus F13 is equal to 1, and F11 is 0 because it is a plane surface, so F12 plus F13 is equal to 1. Now you see, with respect to 1, this orientation of 2 and 3 is exactly symmetric, so whatever is the value, definitely it should be same for F12 and F13, because ultimately how much energy will go strike here and how much energy strike here, definitely these are symmetric, so F12 must be is equal to F13. So if you use this particular relation from the symmetry of the geometry, you can definitely conclude that F12 or F13 must be is equal to 0.5, because their summation is 1 and they are equal. So once you know what is F12, you can easily find out what is F21 using the reciprocity relation, that A1 F12 is equal to A2 into F21. If you use this relation, A1 and A2, you can easily calculate this and this with the given dimension, and since in the perpendicular direction length is same, that will cancel, so you can easily find out what is F21. Okay. Now coming to the third problem, where you have to again calculate what is F12 and F21 and all that. So for that, here this is a cylinder, the two leads 1 and 2. So first of all, with the help of graph, we can find out what is F12. Okay, that we can definitely find out. So here for this problem, given R2 by L and L by R1 is 2, because it was given that L and D are same. Okay, so using that, you first find out from the graph that what is F13. This is 1 and this is 3. So what is F13, that you first find out. So once you know what is F13, then you apply the summation rule between 1 to 2 and 1 to 3. 1 to 1 is 0, 1 to 1 is 0, so F12 plus F13 is equal to 1. Already you have calculated F13, so you just put the value of F13, you will get what is F12. So once you know what is F12, then make use of the formula reciprocity relation, that A2 into F21 is equal to A1 into F12, and you just find out what is F21. Okay, so this is the procedure how we can approach these problems. Here there are some more rules like superposition rules. With the help of that, we can simplify some of the complicated problems to finding out the few factors. You see that if 1 to 2 to 3, if you consider 2 3 is a surface, we can consider this surface as this is 2 and plus this is 3. So the result for F1 to 2 to 3 will be exactly same as few factor 1 to 2 plus few factor from 1 to 3. Symmetrical rule, already we have seen we can make use of the symmetry rule to find out the view factors, as you can see in this pyramid where the base is a square maybe, and you see that all the four surfaces surrounding four surfaces, they are symmetric with respect to the base. So that is why if you apply the summation rule like f11, f12, f13, f14, f15 must be equal to 1, and 1 is the plane surface, so f11 is 0, and all a 1, 2, 1, 3, 1, 4, 1, 5 are all symmetric, and summation of these 4 symmetric values is equal to 1, so each of them must be equal to 0.25. So with the help of this kind of logic, without doing any integration, you can find out the view factors. Okay, so next lecture we'll see the radiation heat transfer. So thank you.